All right, now that we've introduced prime numbers, now we're going to define something else, a different term, and that is the greatest common divisor. So the greatest common divisor of two positive integers a and b is first of all, it's denoted GCD. So whenever I say GCD, that's greatest common divisor, and it is the largest number integer d such that d divides a and d divides b. So it's a common divisor of a and b, right? It divides both a and b. And it's the greatest common divisor, okay? So let's look at a couple of examples. What is the GCD of 8 and 12? Well, 8 and 12 are both even numbers, right? So 2 is a common divisor of 8 and 12, but 2 is not the greatest common divisor of 8 and 12. No. Actually, 4 is the greatest common divisor. 4 divides 8 and 4 divides 12. And there is no number larger than 4 that divides both 8 and 12. So, like, 6 doesn't divide 8. Sorry, 6 doesn't divide 8, yeah, but it does divide 12. 8 divides 8, but 8 doesn't divide 12. And that's as far as you bother checking. GCD of 15 and 12, well, 15 is 3 times 5, and 12 is 3 times 2, right? And so the largest divisor you have from that is 3. So sometimes your greatest common divisor is a prime number, but sometimes, as you can see, it is not. One more example, GCD of 10 and 21. Now, 10 is 5 times 2. And 21 is 3 times 7. So if you have 5 times 2 and 3 times 7, there is no common prime number at all between those. And in fact, there is no common prime divisor between those at all. There's no common divisor other than 1. And so the greatest common divisor of those two numbers is just 1. Let's look at one more example. I said one more on the last one, but for this one, it's going to be a little bit different. Let's look for the greatest common divisor of 1,540 and 490. What is that going to be? Well, how can you go about looking for that? One way is to look at the prime decompositions. And that's kind of what I was hinting at with how I was describing these earlier ones. Let's look at the prime decompositions. 1,540, this equals, and there's different ways of finding prime decompositions. There's algorithms, for finding prime decompositions. In fact, there's one presented in the book if you'd like to look at it. I wasn't planning on going over it in the videos. But I'll tell you, the prime decomposition for this number is 2 times 2 times 5 times 7 times 11. Okay. And then the other number, 490, its prime decomposition is 2 times 5 times 7 times 7. So what you do to find the greatest common divisor of two numbers, if you can write them in their prime decompositions, you look for overlap. So we're going to find overlap between these two. We have a 2. They both have a 2, right? The first number has 2 2s, and the second number only has 1. So as far as overlap goes, we can only take 1 2. They both have 1 5. They both have, the first one has 1 7, and the second one has 2 7s. We can take one of those 7s, but we can't take the second one because it's not shared. And we can't take the 11 because the second number doesn't have an 11. So we're just looking for overlap. So 2, 5, and 7. If you multiply 2 times 5 times 7, that 2 times 5 times 7 is going to be our greatest common divisor. I'm going to put a green box around that one. So that number is 2 times 5 times 7 is 70. It's 10 times 7, right? So 70 is the greatest common divisor of those two numbers. Now, real quick, one more definition related to this is that A and B are what's called relatively prime, also called co-prime, if their greatest common divisor is 1. So that would be the case of 10 and 21, as I showed earlier. So the idea there is basically this is not a claim that the numbers a and b are prime. In fact, neither 10 nor 21 is a prime number, right? You can have two prime numbers, and if you ever take two prime numbers, their greatest common divisor is guaranteed to be 1. So like, let's take two prime numbers like 5 and 19. Yeah, the greatest common divisor in 5 and 19 is going to be 1, because the only divisors of 5 are 1 and 5, and the only divisors of 19 are 1 and 19. So if you take two different prime numbers, yeah, the greatest common divisor is going to be 1. So they're relatively prime, but you can have numbers that are relatively prime to one another. It essentially means that like they don't have any factors in common. 10 and 21 as an example. Okay, so that's greatest common divisor and this sort of spin-off idea of relatively prime. The notion of numbers being relatively prime turns out to be very important in certain areas like algebra. Like if you take abstract algebra, sort of a maybe like a 300 level math class, or 3000, I forget how we do it here. We don't have it at ARCC actually, but if you transfer to a four-year university, you might be able to take a class called abstract algebra. This idea of relatively prime, this is really important when you're studying things like Z mod n, which is that the integers modulo n that I mentioned in a previous video. In fact, I hinted at it with I mentioned this idea of like multiplicative inverses and whether or not they exist. That's related to the idea of relatively prime. Relatively prime is also important for cryptography, so the group studying cryptography is going to have to think about that, as well as one other thing I wanted to mention, which is in linear algebra we're going to be looking at ideas similar to the idea of relatively prime, which we'll get to. Which I'm teaching next semester actually in the fall, so if you want to take it in the fall with me, come do that. It'll be fun.